Hello everybody and welcome back to more of the 2001 Euclid paper put out by the CEMC in the year 2001. We're taking a look at question number 2, which has 3 parts to it. A and B are both light bulbs, which would just mean final answer if we were doing this contest for real. And part C down here requires a written solution. Alright, so as is sort of common with the first couple questions, they don't really seem to be all that connected. I mean, part A, just looking at it's got a parabola, and then we've got these 2 triangular figures here. But, sometimes they have a loose connecting theme, like in question 1, they were all about solving for an unknown value of x, so there might be some theme connecting these questions, but just a pattern I observed that the first couple questions tend to just be a grab bag of different problems for people to solve. Alright, 2a. The vertex of the parabola y equals x minus b squared plus b plus h has coordinates 2, 5. What is the value of h? Okay. So the vertex has coordinates 2, 5, and this equation sort of looks like vertex form of the parabola. So we remember from, well, whenever we did parabolas, I know I did it in 10th grade, but we remember there are several different forms of parabolas. There's standard form, ax squared plus bx plus c. There's root or x-intercept form, which is sort of x minus r times an x minus s, where r and s are the roots, they're the zeros of the parabola. And then there's vertex form, which sort of looks like x minus h all squared plus k, and hk are the xy coordinates, respectively, of the vertex of the parabola. It looks like we have vertex form here, and we're told the coordinates of the vertex, so that might be something we need to be aware of. And will definitely help us. So, looks like we're blue here. We'll switch it back to black. So it looks like we've got vertex form. So what would vertex form actually look like? Well, it would look like x minus 2 squared plus 5. Now we were told y equals x minus b squared plus b plus h. So since both of these are in vertex form, and vertex form is unique, we see b has got to be 2, and b plus h has got to be 5. But we already know what b is, so it's really 2 plus h is equal to 5, or h is equal to 3, and I think we were just asked for the value of h and not for b and h. Yes, what is the value of h? So h equals 3. And that does part A really nicely. Okay. So let's take a look at B, 2b. In the isosceles triangle ABC, so we have it pictured over here, AB is equal to AC. Okay, so we know which angles are equal to make it an isosceles triangle. And we know that angle BAC, so the angle at A, is equal to 40 degrees. Okay. Point P is on AC such that BP is the bisector of angle ABC. So it's the bisector of the angle at B. Similarly, Q is on AB so that CQ bisects the angle at C. What is the size of angle APB in degrees? Okay. So, well, let's draw ourselves a bigger copy of our picture. That way we can add in any of our information, like the 40 degrees at angle A, and see what we can figure out from there. So I want to draw a bigger picture. I'm actually just going to flip over to the next page. So we have A, B, C. We have P over here, we have Q over here. Okay, and we are told A is 40 degrees, and whatever this angle is, this bigger angle is, these two are half of it. So let's call this bigger angle X, and these are each a half X, because BP was the angle bisector. Now because AB and AC are equal, this angle over here must be X, and each of these must be a half X as well. So it'd be really nice if we knew what the angle at B is, and if we knew what angle X is. Well, the sum of the interior angles of a triangle is always 180 degrees. Now we know angle B and angle C are going to have to be equal because this is an isosceles triangle. And we know angle A is 40 degrees. So angle B and angle C, they're both X. So 2x is 180 degrees minus 40 degrees. So that gives us 140 degrees. So x is going to be 70 degrees, and a half x are going to be 35 degrees. So we can actually label that in here. So we'll use blue for what we've just figured out. So we have 35 degrees, and we have 35 degrees. 35 degrees, and 35 degrees. Now, I believe we're asked angle APB. We'll just double check that. Angle APB in degrees. And it looks like the information about Q is not relevant for us. So, at this point I'm realizing, well, the information about it being isosceles and PB bisecting angle B, that looked like that was enough information, we'll see in a moment, to get the triangle. So I'm wondering why the information about Q and C was there. So I'm rereading the question to make sure I haven't made an assumption anywhere. Okay? So AB, AC, those are equal because it's isosceles, so that means angle B and angle C, we can call them both X. Okay? P is on AC, so that PB is a bisector of angle ABC, so that means it splits it in half, because it's a bisector. So we get a half X, a half X. And we already know how to work out X. X got to be 70 degrees. So each of those would be 35 degrees, and then we have angle A, the angle at B, and we would just need the angle at P. So it looks like we don't need any of this information about Q. Interesting. Well, that would make sense. It's just sort of a red herring stuck into a much simpler question. So, question 2, we don't want to overthink it. Oops. So we know the sum of the angles in a triangle, the interior angles are going to be equal. APB, that's the one we want. BAP, well, that's the same as angle BAC. And angle PBA equal to 180 degrees. So we have the angle that we want, plus the angle we were given in the problem, plus the 35 degrees that we just worked out. So angle APB is 180 degrees minus 40 degrees, which is 140 degrees minus 35 degrees. So that's going to be 105 degrees. So I'll just make a very quick statement here. Alright, so that does it for part B. And now we just have our written solution in part C left to do. Alright. In the diagram, length AB is 300. length PQ is 20, and length QR is 100. Also, QR is parallel to AC. Determine the length of BC to the nearest integer. Okay. Well, I'm going to guess that we have similar triangles, but because it's a written solution, we need to justify why we might have some similar triangles in here. Okay? The little handwriting on paper, that means we need a written solution. So we need to explain and justify. It doesn't have to be super rigorous. We don't have to remember the exact names of theorems, but we do have to say we can get this from this, and because we have this, that sort of stuff. Okay? So I'm guessing that we got some similar triangles in here, but let's draw our picture. Bigger copy of our picture and see what I mean. There's B, C, A. Doesn't really matter whereabouts. We have QRP placed. We're not told any information about how far P is from A or anything like that. Now we have some information. We have 100 here. We have 300 as this whole length AB, and I believe 20 was here. Okay. So I think, we were told that these angles are the same here, but I believe this angle here is going to be the same as this angle here, and this angle here is going to be the same as this angle here. Okay, so how would we show that? Well, one thing we can do is we can extend some lines here. We're going to extend QR and QP. Now, since QR is parallel to AC, and the other piece of information we have is that QP and BC are both perpendicular. Actually, we don't need that information. Right, as soon as I know that this angle at A is the same as this angle at R, then because we have the other angles are both 90, we'll get the fact that QPR is the same as CBA from very naturally. So because those angles are parallel, we know that the angle BAC is identical to angle PRQ. Okay. Why? Well, if we have two parallel lines here, and they're both cut by the same transversal, then we know some things. For example, we know that these angles are the same. But anytime you have two lines intersect, opposite angles are the same. So these angles here are the same. And that's the theorem I'm invoking here. Sometimes I've heard it called the Z theorem. But if we look at our bigger picture, here we have QR, and it's making a little Z down here with AC. So now I'm just erasing some extraneous information. We only needed to extend QR. So I'm trying to make my proof a little nicer. So because we have this Z here, because QR is parallel to AC, so the line AB is a transversal for both of them. We're going to get the same angle at A as we do at R. So we know BAC is equal to PRQ. And we know the angle PQR is the same as angle BCA, which is 90 degrees. We're told that in the problem. We can quickly see, just by using sort of the some of the angles in a triangle have to be 180 degrees. That our remaining angle, which is what's the remaining angle? QRP must be equal to CAB. No, not CAB, CBA. QPR, R, not B. QPR, CBA. I really wish that they had labeled them alphabetically. So P should correspond to A, and then R should correspond to C, and Q should correspond to B. They didn't label them alphabetically, so that's a disappointment I have with this problem, but that's okay. Now we can see this really quickly by noting some of the interior angles. It's got to be 180. But each of these angles is identical to another angle that we've seen before, BAC and BCA. So since we have each of these angles are equal, so each pair of angles are equal, then we see that triangle ABC is similar to triangle RPQ. Yeah, C and Q have lined up. Okay, we're good. We're good. Okay, so they're similar. It's fantastic. Now, that means that the proportion of the angles are the same. Now, what were we asked? We were asked to find BC to the nearest integer, I think it was. Let's double check that. Yeah. Determine the length of BC to the nearest integer. So it'll probably be a round down or a round up sort of thing. But BC, we know that it's proportional to PQ, which is 20. We just need to know what the proportion is. What is the ratio between these similar triangles? So we know the triangles are similar, and that means that there is some number that we can scale up each of the side lengths of PQR and get our much bigger triangle BCA. Okay, so we're going to use similar triangles to solve the problem. We just need to figure out what the ratio is. Now the problem is we don't have any that match up. So QR, that side length should be proportional to AC. We don't know AC. We know QR, that's 100. So it's 100 compared to something we don't know. We can't solve that. Same with AB. We know AB is 300. It's got to be proportional to PR, but we don't know length PR. And we want BC. BC is proportional to QP. QP is 20, but we don't know what BC is, so we don't know the proportionality here. So just similar triangles alone will not help us solve this, but we are told that that PQR is a right angle triangle. And we know the two legs. We know PQ is 20, and we know QR is 100. So we can use the Pythagorean Theorem to get length PR. And once we have PR, We know AB is the one it's proportional to, and we know AB is 300, so we can get the ratio of proportionality, the similarity constant there, and use that with 20 from PQ to scale up and get the length of BC. Okay? Confused? Just watch and see what happens, and hopefully things will get a little less confusing. Now, since we know that triangle PQR is right, it's a right angle triangle, then by the Pythagorean Theorem, we know that PQ squared plus QR squared is the length of the hypotenuse, PR squared. Well, that's 20 squared plus 100 squared, and that's going to be PR squared. Well, 20 squared, that's 400. 100 squared, that's going to be 10,000. So that's going to be PR squared. So we can rearrange and say PR is the square root of 1,000 plus 400, so that's 10400. Now we have a factor of 100. Actually, we have a factor of 400 we can take out of here. So we can write it as 400, and we'll be left with times 26. So it'll be 20 times the square root of 26. Okay. So we can use this length, PR, to get the length of AB. Since they're similar triangles, we know that the ratio of BC, that's the one we want, over PQ, that's the length it's proportional to, is the same as AB over the length it's proportional to, which is PR. Okay? So, we know what this proportion is. It's 300. We are told AB is 300 over 20 root 26. Okay? So we can clean that up a little bit. The 20 and the 300, they're going to cancel out. And we'll be left with 15 on top. So it's really 15 over root 26. And now we know the ratio between BC and PQ. And we know what PQ is. So BC, again, the one we want, to PQ is 15 over root 26. But we know PQ is 20. So BC is equal to PQ, just multiplying both sides by PQ. And now we'll substitute in our value of PQ, which is 20. 20 times 15, that's going to be 300, so it's going to be 300 over root 26. That's the value of BC. But we're not asked for the exact value. We are asked to the nearest integer. So this is where our calculators come in handy. So I'm just going to grab my calculator. 300 divided by square root 26. And I get 58.83, which I will round up to 59. So, approximately 58.83. We round up because the first digit to the right is above 5. Well, 5 or above is usually how I was taught. on a question like this, if they ask you a round, they're not going to be really ambiguous and leave it at exactly 5. So these two-digit numbers, this two-digit number is 83. That's above 50, so we round up. That's the way I think about it. Okay. So, on a written question, they don't give you a box to put your answer in. I like to put my answer in a box, so it makes it easier for markers to recognize. Another thing you can do is say, as a little final statement, because sometimes we just look for final statements. Our final statement could be the length of BC to the nearest integer is 59. A nice little therefore statement is also good. Anyway, anything you can do to really distinguish your answer and make it much easier on the markers is an excellent thing to do. So I think that's all we were asked for. Determine the length of BC to the nearest integer. That was it, and C was the last part in question number 2. So that about does it, and I'll see you guys for question number 3 on the 2001 Euclid paper in the next video.